Welcome to the third of our seminars and welcome to our new students. Nice to see you here. Just a note again, these meetings will be recorded and eventually, sorry, I apologise, will be up on YouTube. I just had a hectic week and completely forgot about it, to be honest. But the first 2 weeks were really just a discussion. Things start to get a bit more interesting on this week. So they will be up, promise. Right, so what we're going to just firstly cover is what's required in the next couple of weeks. But firstly, has anyone not received a reply to emails that they've sent in? If so, please raise your hand and let us know. I know that for Benoit, we've got something outstanding there, but we will look to see where that's gone. Anyone else got questions that haven't been answered yet? No? Okay, yeah, still interrupt if you do. You need this fortnight to finalise and submit your IoT presentation. I'll ask Sebash to talk a little bit about those in a sec, but it's due on the 15th of May. Actually, you can talk now about that, Sebash.
Sure. So basically, with this presentation, it's very flexible. It can be you just talking to a camera in a pitch video. It can be you going through some PowerPoint slides. The idea is we want you to think about how would you go about presenting this idea. A very good reference for this would be maybe looking at some Kickstarter and Indiegogo type pitch videos. To see how they present their IoT solution and their digitalization project from a very high level in abstraction, from a concept level. This is going to be due on 15th of May. And just for your information, the mark breakdown that you're going to have for this presentation is focusing on your unique value proposition, telling us what the problem that your IoT idea is trying to solve, a brief explanation of how you're planning to implement that, what are your potential customers, your business model. So you will have, of course, a much detailed version of that as a part of your market research report. But here is a very kind of condensed down version of it in a quick video. We'll be marking it and providing feedback when we receive those submissions. Anything to add to that, Ian, from your end?
Just a hint that if you consider how you would pitch this to a venture capitalist or angel investor, that's the sort of thing we're really after, not a sales pitch, but a benefit and, as we say, the unique value proposition are probably some of the key points in it. This also will help you focus on, excuse me, on your development and get your mindset right for the later parts of it, particularly the implementation and defining of the feature set that you want to implement.
All right. We did cover extensively what content would go in that market research and costing plan in the last seminar. But just for your information, this is also available on the edX page. This would be the mark breakdown for that market research and costing plan, because that's the next submission that's going to be due after the video. So by the time that we're going to have our next seminar, it's going to in the next fortnight. It's going to be due at the end of that, and hopefully we'll submit the recordings from the previous seminar, so we can get a bit more information about the details of that.
Again, I'd point out that the SWOT analysis is very important because in most presentations that you're putting towards a board of management or investors, the first thing they will want to see is the strength, weakness, opportunity, etc., of your proposal.
Of course, just a quick reminder that as we mentioned before, this from this week forward, what we're going to be doing is we will cover a topic of interest, and we'll try to make that discussion, the part that we're talking at you, very short and sweet. The aim is to start an engagement, start a discussion So this week we're going to be talking about sensors, signal conditioning, and energy harvesting. And in the next session, we'll be talking about going from initial prototype and what we call it the sticky tape solution, where we just tape some off-the-shelf sensors and microcontrollers together, and taking that as an initial prototype to PCB manufacturing, kind of getting to that commercialization stage. And our hope is to get the discussion going. Hopefully that if you have any questions in those areas, you can engage with us at the end of that seminar, or of course, will be available via email through that IoT6x mailbox as well. All right. And one more thing before we get to the seminar. The duration for this course, the content and the seminars, we will finish in 12 weeks. We'll just run the MOOC for an extra 2 weeks, so that gives us enough time to go through the final report submissions and have enough time to give you feedback for your submissions. Yeah, so hopefully we can get there together.
There'll be a couple of interesting seminars, what we think are interesting, running during those weeks. So there's still something to join in. Hopefully, after the presentations, we can discuss how far you got, what could be your next steps, offer you any assistance we can in commercialization, and those sort of aspects as well.
All right.
I'd also point out one other quick thing. At the end of this course, it doesn't necessarily mean that we never hear from you again. We do actually have quite a number of students who have kept in contact. I think we talked about the cerebral palsy project in one of the earlier sessions. But we actually do like to know how you're getting on with your development after you've finished the course with us. So happy to keep in contact afterwards, after our 14 weeks is over. Let us know how you're getting on. And I'll be quiet now, Sebash.
Thank you, Ian. And everyone, please feel free to jump in anytime if you wanted to add a comment about these slides or any of the sample projects I show. I want to make it a very fluid discussion. So let's talk about sensors. As a very, very generic look at sensors, of course, we have many systems that require different types of applications. We want to be monitoring a physical, chemical, electrical condition. We can have detectors in our system that can be used as on or off switches. I would say a best way to look at sensors from a digital systems and embedded system IoT point of view, any system sensor that you deal with, it's gonna, at the end of the day, it's gonna have some wires, some control signals, some input output that you would connect to a controller device, and you're reading an information. Okay, so based on that information, that initial information that you're reading from the sensor, sometimes it can be an active component that the sensor is generating. So by the active component, I'm talking about signals, current, a changing current, a changing voltage. So if these are those changes that the sensor is actually capturing, and then you would look at a data sheet and translate that changing current, changing voltage to a temperature, to a pressure, to a physical characteristic. So we have different categorization for sensors. One of them, if we can combine them to active and passive sensors. With active sensors, so as I said, if it's current and voltage that we're monitoring, these are active. And with passive sensors, if it's a passive quantity that we are measuring, such as resistance, capacitance, these would be passive sensors. Okay, but regardless of that, I wanted to focus a bit more on some practical examples, some individual sensor, and give you a quick glimpse of how we interact with them using a microcontroller. And then after we're done with that portion, I'll cover a couple of case studies, a couple of projects that show you the different interactions with sensors that we've done here at Keratin, and hopefully that will kind of help out with your projects as well. So let's get some sample sensors. A very basic one. This is a force sensitive resistor. It's basically a square shaped sheet of electronic device. When you press on it, it will change the resistance that's coming out of those pins. So very, very simple code that we can write on it. It basically set up our void loop. We do an analog read on the pins that are connected. We put a resistor between those pins, connect them directly to our microcontroller, and based on the different value readings that we are getting from the pressure that we're putting on the pad, we can associate a change in the environment or measure something going through a pipe or a couple of different use cases for it, right? And
Little, yeah,
yep.
that's actually quite interesting. And that
Mhm.
particular sensor makes a
Mhm.
reasonable example of it. When you're looking at sensors and what they're designed to do,
Mhm.
that's not necessarily what we end up using them for. One of the great exciting things about working in an IoT is using sensors for things they weren't originally designed for. So if we look at that force resistive sensor, it's just a flat plate and you push down on it and you measure the force that's being imparted on that particular sensor.
Mhm.
We can also use it, believe it or not, for measuring joint angles. Now, that's simply because if we place the force sensor, say, across a finger and we bend the finger on the inside or the outside, doesn't really matter, we're imparting a force on that resistor. The more we bend the finger, the greater the force that is going to be on that sensor. Therefore, we can interpret those results and extrapolate from the force on the sensor what the angle of that joint is. In this case, it wouldn't be terribly accurate, but for something like a gaming application, it could actually work. And this is applicable to most sensors, that you don't just look at what they're made to measure. You start to think, well, I need to measure this. What other attribute of the environment or the action would give me that information? Measuring salinity in water is another really good example. We don't measure how much salt's in the water. We correlate the conductivity of the water to the saturation of salts. And this allows us to do a far wider range of things than we can with just using the sensors for what they were designed for. Sorry, Sebastian, you can go on
No,
again.
no, no,
I'll
no,
keep interrupting.
definitely. No, another example of that I thought about is for a project we needed to see how I have to abstract it out a bit so we don't give away the concept too much. But basically, we needed to look at a door being open or not in a pipe, and the way we found the door being open or not, we ended up using an electromagnet with a Hall effect sensor that was looking at the magnetic field around the sensor. And so the sensor wasn't designed to detect whether that pipe is closed or open, but it was designed to get the magnetic field and present to us as a numeric value. But based on how far off from the magnet we are, we could determine how the door is open or how far the pipe has opened or not. So another example of using a sensor for a different purpose that was originally designed for a different purpose and in a different project. So and that's the fun thing about sensors, especially in the digital area, is they're usually quick to get to work. So here's an example of a temperature sensor. Basically, this is a TMP36. It has 3 pins. If you want to read information from it, it's a very simple connection. There's a voltage, there's a ground, there's a signal pin. We simply do an analog read on the pin that's connected to the sensor. And basically, we look at a data sheet to see that raw data value that we're reading. I have it in the next slide. The raw data value that we're reading, how does that get translated to an actual temperature? We put that equation in the code, and that simple reading gets translated to temperature. Another sensor that we really like to use with our research group is called IMU. IMU stands for Inertial Measurement Unit. It's basically an accelerometer, which gives you linear acceleration, magnetometer, which gives you the magnetic field, and a gyroscope, all embedded on the same device. So they're either on the same system on a chip package, or they could be 3 separate chips on a single PCB. Now, what we do with IMUs, and you'll see in a couple of project examples, each of these sensors will provide an XYZ. Okay. Now we use sensor fusion, and we go with these 3 sets of XYZ, so with these 9 initial values, to a coordinate system. An example of that is Euler angles. Basically, we fuse these 3 different sensors together to get to a pitch, roll, and yaw, and this will give us an orientation of the object in a 3D space. Another way that we can represent this information is using quaternions, which will give you 4 imaginary numbers. And a simple way of explaining quaternions is it basically gives you the probability of where the object is in that 3D space, and it's just a different way of representing orientation of an object. So with IMUs, we use them in a lot of projects. I'll show you the example of how we use them for capturing human movement and dog movement and capturing wrist movement. But on its own, as we said, so IMU on its own is for capturing orientation, right? But we have use cases where we put an IMU on a patient's chest and try to capture heartbeat based on the vibrations that and the expansions of the chest cavity. Or people have again used them on water pipes to look at what vibrations in there. So they're very versatile, especially like a very big interest area in using IMUs is in human capture. And Ian and I, we work in a lot of assistive technology type projects. So anything from human movement to imagine the angle that a hospital bed would go up and down to the angle of a wheelchair cushion as you go through a ramp, we can capture it with an IMU and apply it as one of the very useful sensors that we can have. Because traditionally, lots of people just use an accelerometer or a gyroscope, and then or a standalone gyroscope and fuse that information together. But if you have a full-on IMU where you have the magnetometer, gyroscope, and the accelerometer all providing you that orientation information, we can do a lot of more interesting things with it. One more concept before we move on to the sample project is the concept of signal conditioning. So basically, as a very quick overview, the initial signals that you're reading with from these sensors, for it to be usable for you, you might have to make some changes for it. So there's linearization. So if you have a signal and you wanted to see a change in that signal in a more linear fashion, we'll apply linearization on it. Something that's probably more familiar with people is amplification. So amplifying the changes in the signal so we can see it better, detect those events better. And a very useful one that we have to deal with a lot is filtering, because it's not only filtering noise out of your initial signal, but it's extracting different type of information from your signal and different characteristics and different things that are happening at different time throughout your data collection process. We'll do some filtering to detect those different events, right? So let's talk about some sample projects. So you can see my wife's head cut off here. So this is part of my wife's PhD. She's working with people with vision impairment, and this is part of a remote orientation and mobility training. So people with vision impairment, they either use a white cane or a walking guide dog. At the moment, imagine if you want to go to a new location and you already know how to use a white cane, you know how to use a guide dog, but for you to go to a new location, say if it's just a one-off shopping center, you have to get a trainer from the training center to go with you on that path. You have then memorize that path so then you can go there independently, either using your cane or using your guide dog. So the idea of this project is let's do this remotely. At the moment, the images you see here, and I'll show a video afterwards, we have an IMU connected to a white cane, one IMU connected to one of the legs, and we would be remotely monitoring how the person is using their white cane. And of course, there will be GPS location and for indoor navigation, other solutions, and remotely determining the pathway for that person. Now, we use similar sensors for capturing the movement of their guide dogs if they were using a guide dog, and then potentially be able to see if the dog that they're using is developing any sort of lameness or limping. Okay, so but where did we start with this project? It was uh, getting a bunch of Arduinos and sensor kits and Bluetooth modules and IMUs and literally sticky taping, taping them together like this and building a transceiver sender receiver system where we would be transmitting this IMU information via Bluetooth initially. And then having another Arduino module with a Bluetooth dongle connected to it to capture the information. We eventually moved on to using this another off-the-shelf kind of an all-in-one embedded solution, Xsense Dot, which comes with its own mobile application where we can monitor the data coming in. So here's one of our data collection session where you can see one of our students very extremely not correctly using the sensor, using the white cane. And we've kind of synchronized that video from the data on the top Euler angles and the bottom. So both of them are Euler angles of the leg and the white cane. What this would be telling us is once we capture a lot of data, we can then start applying things like machine learning and event detection, signal processing techniques to determine how accurately they were using the cane. Where they, because with this specific white cane, this 2-point touch method, you can see my wife's head creeping in. With this specific method, you have to put your foot on the place that you're tapping. So you tap and then you put your foot at the same place. And then IMUs are helping us capture that movement. Another project in the same context, but this time for people who are using their guide dogs. And because with the guide dogs, they will always be wearing this harness. We have them put the IMUs on the harness itself, and we will have a 360 degree camera connected in the middle of the harness. And just moving on to the video portion of it, as the dog is walking, now you can already see from the bottom signal how that filtering is going to become very important here. Because this is just the raw sensor data coming in, and we're monitoring the behavior of the dog. So the sensor that was designed for getting orientation, we're using it to detect the front paw, back paw movement of this guide dog, then visualizing the orientation of the harness at the bottom left side. And then once we have the 360 camera implemented in there, that 360 footage would be passed through to a base station. Our trainer would put on a VR headset and remotely guide the person how to where to go and if there are any dangers coming in. Now, because the trainer is not when they're there, they would be also checking on the dog itself. We would have other sensors such as digital microphone to pick up the breathing and the heart rate of the dog. So if there are any kind of danger signs that would potentially not get picked up by the owner, we can pick them up and find any sign of limping and lameness down the line. So
Before you move off that
yeah,
screen there, Savash, if
yeah.
you look at the little illustration in the bottom left-hand corner, that's the loop of the harness. We can see the IMU on top. And by watching that, you can actually see that there's a rhythm, slightly angled at the moment. So from that, we can interpret that the dog is sitting. Now it's standing because it's more vertical. And if you look at the way it moves around the different axes in yaw, pitch, not so much roll, the roll we get with the sitting. Yeah, sorry, pitch we get with the sitting.
Yeah.
We can then extrapolate from that information and work out which leg is moving forward at what time. Look for symmetry of those movements. So if the dog is getting hip problems in the back leg, for example, we can pick up there's a lack of symmetry in the back leg movement, and then work out that there may be something wrong with the leg. I'd point out also the reason we're doing this is these dogs cost in the vicinity of 60,000 Australian dollars, which would be what, 40,000 American dollars, and I can't think of it in euros, but anyway, a lot of money. So we need to take care of them, and we need to keep them working as long as possible.
Mhm. Yeah, they cost as much as my salary, I guess. moving on to another interesting project. So this, we're calling this one gamification of rehabilitation. This is part of my own PhD research. Basically, if you're not familiar with rehab type exercises after an injury, or if for people who suffer from muscle disorders, there are these repetitive rehabilitation type exercises that you have to go through. A very common rehab exercises after a wrist injury or a finger injury, where you have to repeat these very repetitive type exercises multiple times throughout the day. So our idea was, let's use IMUs again to capture wrist movement in real time. And then because we got to capturing that movement in real time, we ended up thinking, okay, now that we're getting this movement in real time, let's build some games around it, both from an engagement point of view, so that there is some sort of interaction that's going on. So we're not just dryly doing the exercise, especially for the younger kids, so they become more engaged in in doing their exercises, and also for the clinicians, uh, it would be a good way of capturing what we call active range of movement. So when your hand is actively moving, and of course these days you have expensive motion capture setups that we can get very accurate full body monitoring. But the idea here is that we wanted something portable in an IoT type solution that they can take with them at home. They can do the exercises, and of course, there are already entertainment sort of exercise games out there, like a Nintendo Wii Fit, Nintendo Switch Ring Fit Adventure type thing. But the different thing that we are doing is, while you're interacting with those sort of setups, we are providing data that's clinically accurate. And I'll show you a glimpse of how we did some of the validations for it. So again, similar to the other projects, this is where we started. Get literally starting with putting on some prototype boards together with a battery, then having a sticky tape with a literal sticky tape on top of it on the other side to capture the IMU data. And then the next step of that, we're kind of designing a standalone PCB that includes some of those just the chips in there, so you can have an all-in-one solution similar to the off-the-shelf. And one of the reasons that we want to just go and use a IMU solution for these types of projects is because most of the time, these IMU off-the-shelf solutions, they don't necessarily provide you the raw sensor data, so we don't know how they're fusing that information together and how much data loss we have in that conversion. So that's why we usually start with the very raw sensor data, literally reading the ADC values and then converting them to acceleration gyroscope information, and then fuse them together ourselves. So an interesting slide I think I put in here to just to give you an idea of how we go about usually validating sensor information in this more of a medical field, is because accuracy for us is important, right? Even though we already know it's not realistic to, especially because for this project, some of our participants are children with cerebral palsy, so we can't expect them, the parents, to take their infant to a motion analysis lab that's like multi-million dollar motion analysis lab outside their home to do just some basic testing. So just to show the accuracy of it, we put these reflectors on, and then we captured some data in our motion analysis lab, and I'm drawing the data that we're capturing from the IMU, which is that orange line, versus the blue line, which is captured from the video setup. Just to validate, and I've kind of shifted the data a little bit so we can see how close the signals would look like. And that's how we validate the accuracy of these types of solutions. So some videos to show you here. So basically, because we were getting that real-time information, a couple of things that we were doing is we were transmitting that signal as a Bluetooth communication, and then we're visualizing it in Unity in real time. And the IoT aspect of it comes from, we can also set it up to be transferred as a UDP package. So when you're within a hospital environment, they could be just the patient could be just in a different ward doing some movement, and their orientation data and movement data would be directly seen by the clinician on our side of the hospital, or even a different hospital. And kind of getting that idea even a bit more out there is when you're at home and you're doing these exercises, they literally just give you a piece of paper that you're supposed to use and you do the exercises, and you don't know how accurately you're actually doing it and what are the threshold that you should be aiming for. So because we have that real-time orientation monitoring, so we built this sort of setup that as the sensor data comes in, if you go outside a particular threshold, you can see how far where you are, and then how long it takes for you to be in that area. So
A quick point. Oh, sorry.
yeah, go
Finish
ahead. Yeah.
first. I was just going to say, back on that validation point,
Mm,
it's critically important that people understand the importance of validation.
mm,
We do a lot of work in the mining industry, and one of the large problems they have in their process facilities is dirty data. So they're trying to make decisions on data that isn't necessarily correct, or is noisy, or is corrupt, or inaccurate. So the ability to be able to validate what you're sensing is critically important in proving what you're doing is actually worthwhile. So when you're designing a system and you've created this sensor that you think is measuring some event or some environmental variable, uh, try to think of a way where you can validate it against some gold standard or some known method, to show that your way of sensing it is actually accurate and up to the standard that's required for that particular industry.
mm. Definitely, I would just add to that these days the concept of digital twin is a very kind of a buzzword, I think that everyone likes to use in the context of Industry 4.0. But all these digital twin ideas, if the initial data that we're capturing and using to build that digital twin is dirty and it's not accurate, then the digital twin is going to be very useless as well. So that's why, as Ian said, like it's very important that the initial data that you're collecting from the ground up, that's been validated first before you move on to these different aspects of your project and do the data analysis and machine learning and digital twins and that sorts of stuff.
And
Um, yeah.
the old adage of garbage in, garbage out.
Oh, God. Yeah. So just a couple of examples that I put here to show you. So getting that idea of monitoring and applying it to a full body monitoring for a patient. And speaking of mining, similar thing. Now doing kind of full body monitoring. To this time, look at posture, and these are all again using IMU sensors connected to different parts of the body. That data being transmitted real time. Doing a little uh, hip dance for you here, just testing some IMU information, and then at the same time, kind of measuring the orientation of this IMU data as a part of a monitoring system. So moving on to the next part of the discussion, one of the things that I found very useful when I actually started working with sensors myself is these these kind of sensor pack type devices. There are a couple of very good IMU versions of them that recently, sorry, Arduino version of them that recently come out, like the Arduino Nicla Sense and the Arduino Nicla Vision. These are basically usually a microcontroller combined with a couple of extra sensors in there. And the good thing about these sort of devices is they usually provide the hardware and the software as open hardware and open source. So you could potentially start with something like this, uh, play around with a couple of sensors, and then uh, start from that design and design your own and remove the ones that you don't need. So I just put two examples here, the simple link sensor tag, and then another one is the Nordic 52 thingy. Again, comes with its own app, some microphones, some different types of sensors in there. Could be an interesting starting point to get an idea of a development board with a bunch of sensors in there and what sort of thing that you can do with them. Um,
And we'll be looking at how to reduce these down to custom boards next week. I think you said, Savash, correct?
yeah, it's next
Next fortnight.
fortnight. Yeah. So just finishing up this seminar on a quick look at energy scavenging. So with embedded system and IoT, there's usually the chance that these sensors that we are putting in, uh, we need them to be actually using the environment around them to scavenge some energy to power themselves on. Otherwise, it wouldn't necessarily be cost effective to actually make a part of an operation smart, because as soon as you add the cost of, okay, you need to have people go there and replace sensors or replace batteries and add the maintenance costs, it's going to add a lot in there. So that's why energy scavenging is important. So we have, of course, different types of energy scavenging. So the traditional solar power, wind power, human motion, and radio frequency as examples of it. So I thought I'll included a couple of like interesting examples. Like this is found this in someone's blog. I put the name up there. So this guy was saying, oh, he always went for a run in the morning, and his his iPhone was getting pretty old, and it was running out of battery as he was listening to the music in that morning run. So he ended up scavenging some some electronics from a light bulb, used these piezo electric sensors in the shoe inlay to use the kinetic energy of when he was walking and running to charge up his phone. And he's posted this whole project and all of the sample files in his blog. So if you search for Abel Haynes shoe charger, yeah, the blog will pop open. It's an interesting read the way he's done it. Then there's the more traditional hydroelectric type generators using these turbines to generate energy and scavenge energy, or these they're on a much smaller scale in that microcontroller Arduino type solution. These water turbine generators have become pretty popular as the test cases, and they usually come with some flow meters in there and use the flow of water to generate some energy that you can test. And there are all these more commercial ones that have actually become available, being marketed towards people who like to go camping. So with these sort of setup, uh, and it's an interesting thing to keep in mind. For example, one of the projects that we're working on is a smart PPE for people who are working in a hostile environment. So it's all nice and good to have sensors to capture behavior, say hydration, body pressure, posture, that blood pressure, posture, that type of information. But all these sensors, they would require power, and there's already equipment that the miners would be wearing. So we don't want to add too much of a chunky battery in there. So one of the things that we're exploring is trying to use their kinetic energy, because especially these are underground miners, so we can't just use a solar panel because there's no sun underground, right? So uh, use different methods to harvest energy around, and then build the IoT solution that way. And then I'll just finish up this discussion with just a quick thought. With energy and performance and battery consumption and performance, there's always a back and forth between what we're getting, right? So the less energy that we are consuming and the more low power modes and battery saving modes that we're using, the more low performance our sensor and IoT solution is going to be. And then, well, the more high performance it is, and the more performance that we need, it's going to consume a lot more power, right? So there's always a constant back and forth between how we're deciding to use these sensors. When do we use them? When do we actually need to transmit that sensor information? Let's say if you're monitoring a water main, how often do you actually need to transmit that information? Do you also do you only send that information when you reach a certain threshold, or do you constantly send? It's a more critical, say, a temperature monitoring system in a power plant that's a bit more critical, and you need to have that information faster. So a couple of interesting considerations when we're dealing with sensors and embedded system and electronic side of the IoT that that I think are pretty interesting.
Yeah.
And
I'm
anything
sorry.
to add to that, Ian?
Yeah, I was just going to make a comment on the power consumption. It is critically important because in a lot of these IoT devices, we want to put the device out in the field, and in the field, there's quite often a limited access to power. So we just go to battery power. In many cases, we can't use solar power because it's shaded or it's indoors or many other reasons. So maintaining that balance with the processing power, transmitting power, and that's very important when you're looking at radio communication, and choosing the right sort of protocol to minimize your power consumption is critically important for many applications. On the energy scavenging side, we had a really good example of a project that a friend of mine worked on. If you want to look it up, it's Malatar Wirasingi. He's in Sri Lanka. But he developed a system for warning of elephant encroachment on human habitation. Worked perfectly when we tried it in Perth. We didn't get any elephants on campus. Uh, but in Sri Lanka, elephants going into villages and destroying crops is a real threat. So what they wanted to do is track the movement of the wild elephants. Now, as you can imagine, you don't want to be capturing these elephants to change the batteries every month or two. They're out in the wild and they're not very friendly little things. So he used energy scavenging as a way of boosting the battery performance and getting uh, the device recharging from the motion of the elephant's ears where these tags were. He then had to have a very low power transmission protocol to send the signals from the remote jungles in Sri Lanka, where there's no phone coverage, out to base stations and trading off the information he was capturing from the elephants, the amount he could capture, and the amount he could transmit given the power he was generating from the energy scavenging. So it was a really good project in looking at balancing processing power, communication, bandwidth, and energy consumption all in one neat little project.
Mhm. Looks like we have a question from the panel. Mahmoud, yeah, please go ahead, ask your question.
Yes, thank you for your information. Knowledge. I want to ask, I am coming from like industrial networking background. So usually when we have some new devices, it comes through validation testing lab, like global one to validate this one. So is it the same for any new sensors, or if I add a new sensor for existing device, it go to some global lab to make the validation for this new sensor as a type test?
Sorry, I think the last part of your question got cut out.
Yeah, as a type test, this like to identify this sensor is for what and the accuracy, like to get it approved for global market.
Is your question about what the validation processes are like?
Yeah, validation process
Mhm.
globally. Like, is there like an agency or a global laboratory to make this validation?
So that's a good point because we had a company reach out to us specifically about some hydration type sensors, and they wanted us to validate because there are these products out there saying, "Oh, we're getting hydration, very nice. You just put a wristwatch and we'll give you hydration." And this company wanted exactly that question answered. So in an academic setting, how do we go about that? So what we do is a good validation technique is you capture that sensor data and you validate that against more traditional techniques that have been already been proven. So in this case, we captured that data and validated it against urine analysis and sweat analysis and that type of information. And it turned out, well, no, these products weren't necessarily giving you the accurate information that they were claiming. Uh, I would say it depends. Things get a bit more complicated when you get some safety medical standards in place as well, because then the level of accuracy that you would need for a certain from a certain sensor and the failure rates that would be acceptable would depend on the application area of it.
Yeah, there's usually multiple accreditation areas.
Hmm.
So if you were looking at the components, you might be needing to do environmental testing. So what conditions can the devices be worked in? And then if it was in a medical situation, you've got a whole bunch of regulations that would then you'd have to meet, which may or may not be to do with accuracy. It may only be to do with safety. And we've got a biomedical engineer here with us, so he could tell us lots about that. But it varies for each industry. Universities are usually a fairly good place to make a start. They've usually got the equipment, the resources, and the people to validate in a given area. So we validated the motion sensors with our health professionals, so physiotherapists, occupational therapists, and those people who basically set the standard for what normal range of movement is or accuracy of movement.
Okay, yeah. Then, like for example, like Cornell University, like issue like some kind of report or test certificate that this kind of sensor will fulfill some kind of standard or some kind of applications. So the manufacturer or the producer of the sensor can proceed with the next step, right?
Yeah, I'm not sure that you'd always get a certificate, but you would get a report. You get a report that this device meets this particular standard, or this device has this level of accuracy, or it performed as per specification in this environment. And because universities are generally independent, it's quite often taken as proof for certification reasons.
Okay, got it. Thanks a lot.
No worries.
No problem.
Anyone else? Any comments, questions?
One suggestion, just on the sensor side of things, if you have a bit of a think of what you are trying to measure if you are using sensors, in the next session after we had the chat, you might want to just raise, well, I'm using this particular, or I want to read this particular attribute. We could discuss which sensors may actually be good for that that application. Have a look around to see what's about, see if there's something that will directly measure it. But again, great thing, really interesting thing about playing with sensors is using sensors for what they were not initially intended for. Yeah, we've given some examples of that, but with the hydration, it's using conductivity measure for level of sweating, so we can look at surface hydration levels. Using bioimpedance to work out what the core hydration is within a body, because the impedance of cells is different for fat cells and the water cells and the muscle cells. So you put different frequencies through the body, measure the impedance at those frequencies, and it gives you the water composition and fat composition of the body. Sort of. It's that great, but it's sort of okay.
And I think there's a point to be made in terms of the level of because sometimes with these indirect measures you might not get the actual value, but you might get trends in something. So it might, for example, specifically hydration, what we found is some of the methods like the BIVA method or that impedance, looking at changes in impedance, they don't necessarily give the traditional classical hydration. There are huge gaps in there, but they still provide a trend in hydration, and they can provide whether you're going the hydration levels are going high and low. And in some application areas, for example, with the in mining, most of the interest is well finding that trend, and if you're getting towards a low trend, they want a warning system so that you go and drink some water. So yeah, it's a very fun area. I was just thinking of again indirect ways. Some of those garbage smart garbage cans projects that we were looking at, and the different types of sensors we were thinking of putting, say, at the bottom of the garbage bag to determine how full it is, or there was a specific, was it the gas sensor we're using for
Yeah, it was a
something?
gas sensor looking at the kind of gases being given
Yeah.
off, so we can tell if there's rotting garbage emitting
Yeah.
a bad smell, which means you want to go and empty the bin more often. And we could always go back to our horse mucus measurement. For those who didn't hear that one, we had a vet that developed an IoT device looking at horse health. And one of the attributes that's important is the colour of a horse's mucus. And that reflects a lot on its condition. So part of his project was to develop a sensor that would measure the colour of horse mucus. And that was just done through light, but fun things you can measure. All right, well, if there's nothing else, we're just about out of time. Nothing further from anyone? You're a very quiet mob. Oh, there we go. Ahmed. Oh, good.
Just one more question regarding the presentation. Is there any recommendation for the video settings? Like, should we put some kind of logo or some kind of settings for the video, or it's okay for anything?
It's fairly flexible, I would say. So again, it can be you recording a PowerPoint presentation. It can be literally just a camera pointing to yourself as you're talking. We're very open.
Yeah, it's what you're most comfortable with.
Yeah.
Okay, great. Thanks.
No worries.
Benoit, did you have something to say?
I just because I don't know if we talk just now or after the just two of us about how to should I send you the MyLet Canvatizer and so on.
Sure. So for those submissions, we can talk right now. For those submissions, because the way edX works, after the due date, it doesn't allow sometimes doesn't allow you to submit something. Just email them directly to us, and then we can manually then go and change your grade. So we've had two submissions. So we had the Canvanizer, the video one due at the end of this week, which well you'll get an extension for that because you enrolled a bit late. But yeah, but when you submit those, you can just send the link to us directly, and we'll take a look at it.
Okay, so if I'm fast enough, I send you the Canvatizer by mail and the video by HEDX.
Yeah, so with video, what you can do is if you maybe post it as an unlisted video on YouTube, so then you can just send us a private link that way, or any other kind of sharing platform, and then yeah, I'll every couple of days I'll go and try to respond as many of those questions as I can, and then we'll get back to you.
Okay, thanks a lot.
No worries.
Okay, I'll stop the recording now.